In this example, the Cooper family is rafting on the Wolf River. The river is 150 meters wide and flowing south at 1 meter per second. In still water, the raft travels at 5 meters per second. Part A, we want to figure out how long it will take to travel from one bank to the other if the raft is headed for a point directly across the river. So the answer to part A is pretty easy. We don't even need to use any vectors. Remember that this is not relative to the land. This is just how long will it take to get from one point to the other point. And so in still water, the raft travels at 5 meters per second. And all we really need to do for this one is take 150 meters and divide it by 5. And that'll be meters per second. That'll leave us with seconds. So 150 divided by 5 is 30 seconds. So occasionally, if you're asked one of these application problems, if you read it, you really don't have to use vectors maybe for some of it, but for each one of these you're going to have to use vectors eventually probably. Okay? So the first one is, it's going to take 30 seconds. How far down the river will the raft land? Well, this one gets a little bit more involved, but if we take a look at the current is flowing south at 1 meter per second. So let me draw a little picture here. It's a really, really good idea with these to draw a picture. Very important. So there's the current, and it's flowing this way at 1 meter per second. And you've got this raft here, and it's going that direction at 5 meters per second. So for every second that passes, the raft will both move 5 meters this direction and also 1 meter to the right. So if we're asked to find how far down the river the raft will land, we can simply take the time it takes to go across the river, which is 30 seconds, and then multiply that by 1. So the answer to this one will just be 30 meters. Again, no vectors needed for this one. The velocity of the raft relative to the shore, that's a little bit trickier. So we do need to use vectors for this one. What we're looking for is we're looking for the resultant magnitude when you apply the current and then the forward velocity. Because if you're a bystander just over here on one side of the river, the raft will move towards you if you stand right here at a speed that's probably going to be greater than 5. So let's see if we can figure this one out. You've got the current here at 1 meter per second, and the raft is heading directly across the river, so these two vectors will be perpendicular. In this case, from example 1, we actually don't have to find the x and the y components because we're already given the x and the y components, which is kind of nice. But we do want to find the magnitude. So if you think about this, the resultant vector is going to be this one right here. If you look at it geometrically, remember you can use the tip-to-tail method, or you could use the parallelogram method. But either way you cut it, you're going to wind up with this guy in green. So that forms a right triangle, and if we do a little bit of math on this one, we've got this magnitude here being equal to the square root of 5 squared plus 1 squared. So that's the square root of 26. Now, this is an application type problem, so you're probably not going to tell someone, oh hey, you know, this raft is going to approach you at the square root of 26 meters per second. It's great to find this exact value, and that's super awesome. However, what we probably will do is round this. So let's round this to the nearest tenth, and that would be 5.1. So this is about 5.1 meters per second. So there's your solution to C. The current is helping a little bit, not much, but a little bit.